Hi everyone, it's me Ui. I would like to share about the flight dynamic and control of paper aeroplane that all of us can make it at home. Before we go deeper, what is static stability and what is dynamic stability? Static stability is the tendency of aircraft to return to its equilibrium state after a disturbance, while dynamic stability is concerned with the time history of the aircraft motion after being disturbed from its initial equilibrium condition. So, an aircraft is considered statically stable if the Cm alpha is negative for pitching motion, and Cl beta is negative for rolling motion, and Cm beta is positive for yawing motion. For dynamic stability, if the root is located at the left half plane of the root locus plot, then it is dynamically stable. To understand longitudinal static stability and dynamic stability better, we can do pure pitching experiment. In a pure pitching, we assume the center of gravity of airplane is constrained to move in a straight line and a constant speed. Number 2. Airplane free to pitch about its center of gravity. So, we can make a wing-only configuration paper plane by following these dimensions. Of course, we need to calculate the location of aerodynamic center as well. So, yep. So, this is what happened to the paper plane without any weight ballast. We can observe that the paper plane rotates continuously in a positive pitching movement direction. So, what is happening? So, we need to calculate the location of AC and CG to see what happened. From the calculation, we found the leading edge CG location. We found out from the leading edge, the CG location is behind the AC. This causing that Cm alpha become positive, which is unstable. This means that when the angle of attack is increased by disturbance, the paper planes tend to develop a positive nose-up pitching movement that would further increase the angle of attack. This explains why paper plane rotates continuously in a positive pitching movement direction. So, adding weight ballast in front of the wing will cause the CG location to be in front of the AC, which will make the Cm alpha become negative. The equation to calculate the Cm alpha is at here, where the Cm alpha for wing for thin aerofoil is 2 pi radian, but we need to correct it with its aspect ratio. Then, so having a negative Cm alpha means the paper planes will apply restoring moment when the paper plane is disturbed from original equilibrium or trim condition. So this is what happens when you have a ballast and without ballast. You can see if you have a ballast, the airplane tends to fly smoothly because it have a restoring movement when being disturbed by any disturbance. Now, let's generate the motion in MATLAB. As we don't have any elevator control, so we just put 1 at the numerator, and we can see the pitch angle with no ballast diverge with time, which indicates the system is unstable. Oppositely, the paper plane with ballast, the oscillation of the pitch angle decay with time and indicate that is dynamically stable. We also can know the dynamic stability by looking at the roots of the characteristic equation. To get the characteristic equation, we can equate the denominators to 0 and factorize this equation will give us eigenvalue or roots. With the roots, we can know how the airplane behaves. For the paper plane with ballast, the roots are complex conjugate with a negative real part, and the negative real parts of the complex roots will produce decaying sinusoidal oscillation, and the imaginary parts will affect the periods of the oscillation, since both of the roots are located at the left half plane of the root locus, so the paper plane is dynamically stable. Now, we already have a basic understanding of the methods to determine static stability and dynamic stability. Now, we can build and design our own paper plane. A simple paper plane will need a tail, a wing, a control surface, and a ballast. So, let's look at the video to learn how to build your own paper plane.
Hi everyone, it's me Ui. Today, we'll make a paper plane. So, the material that you need are a paper cardboard, a satay stick, and a weight ballast, which in my case, I will use rivets. So, first, you need to cut this down, the wing and the tail. So, let's make it. Boom! And this is my paper plane. So, I have 4 rivets as my weight ballast. Why? Because at first, when I'm having two rivet, my CG location is at here, which is behind the AC location. And so after that, I add 2 more rivet, which make it 4 in total, the rivet. And now my CG location is in front of the AC, which will assure the static longitudinal stability of my paper plane. So my question is, how can we find the CG location? So you only need one tool, which is a pen. So this is your paper plane, and you put on top of the pen and find the location where you can make it stable. And here is it. Here it is, my CG location at here. So it should be stable. Thanks for watching. See you next time.
So, this is my first generation of paper plane, which the wing and tail are made of grey cardboard. Before that, let's look at how it flies. So, as you can see, I realize the plane is unable to fly well sometimes, and if you observe carefully, you will see the wing tend to bend upward when in the air. So, this might decrease the lift as the effective wing surface area becomes less. So, I think I should find a better material that is more stiff than the grey cardboard. So, I redo the plane with corrugated cardboard with wing and tails. I still use the grey cardboard at the control surface, as it's easier to deflect them if needed. So there are a total of 6 rivets as a weight ballast, so the center of gravity is far in front of the AC location, which make my aircraft more stable in a pitching motion. So now, how should I determine the plane is statically or dynamically stable? I need to form a state space equation. So I need to get the mass moment inertia and the CG location, which can be easily found by using SolidWorks. But you need to be careful with the material you use and also the direction X, Y, Z axis. The static stability of the design paper plane can be evaluated by looking at the values of the stability derivative. So I summarize the stability derivative for my paper plane, and I found the Cm alpha is negative value, so my pitching is stable. The Cl beta is negative value, so the rolling is stable. The Cm beta is a positive value, so the yawing is also statically stable. Then, we can generate the state space equation for longitudinal motion by substituting the stability derivative. The matrix will forms in the forms of x dot equal to ax plus bu, where A is a state matrix, B is the input matrix, and X is a state vector, and U is a control vector. You can either manually transfer the state space equation to transfer function, or using the equation as shown above, or use the SS to transfer function command in the MATLAB to convert the state space equation to transfer function. So we can get our transfer function for pitch angles over deflections at elevator. And the figure depicts the pitch angles theta of designed paper planes due to negative input at the elevator deflection angle. So from the graph, the oscillation of the pitch angle decay with times, and the rates of decay of the oscillation can be shown by the time for halving the initial amplitude of the disturbance, and the system is stable as the oscillation diminish over time. To determine its dynamic stability, we can also use the root locus plot. The location of the root is the root locus plot. The location of the root in the root locus plot will tell us how the plane behaves. So since all the roots are located at the left half planes of the root locus, so the paper plane is dynamically stable. At the meantime, we can identify the short periods and the forward motion appeared in the longitudinal motion. So short period has higher frequency, and the distance from the origin to its root is frequency, so it should further away from origin for short periods. So here's the root for short periods, while the other one with lower frequency is the forward motion. The characteristic equation can be obtained by equating the denominator of the transfer function with 0. So equate these with 0, we get a characteristic equation of the system. And the eigenvalue of the roots from the characteristic equation will show us the behavior of the plane. By knowing the root, we know its damping ratio, its frequency, its time constant, and the mode. So we had knows about the oscillations of the pitch angle decay with time, but how do we know the rates of decay of the oscillation? And yeah, the rates of the decay is equivalent to the time to halve, and the degree of dynamic stability can also be specified by the time to halve. So this means that the paper plane has a high degree of dynamic stability as the short period for the time to halve is very short. Now, let's look at how well the control surface work at different frequency or different motion. So, we need to understand the frequency response. Frequency response is the magnitude and phase relationship between inputs and output signal. So it's like how effective is a control surface performed at different frequency to produce a certain output. The information of the frequency response is shown by using a Bode diagram. So from the Bode diagram, we can see the peaks of the amplitude ratio occur at a frequency of 1.38, which is also the frequency of forward motion. As the frequency increases in the Bode diagram, the amplitude ratio becomes smaller, and this indicating that the elevator has a negligible effect on the pitch angle at higher frequency. So short period motion with a frequency of 24.6 radian per second is fall within this high frequency range. So we had evaluated the longitudinal motion, and now let's look at the laterals and directional stability. Same as previously, we will substitute the stability derivative into the state space equation, but be careful at here. We need to make sure that the stability derivative L beta times NR is larger than N beta LR. This is because the spiral mode is considered stable if L beta and R is larger. A stable spiral mode means the paper planes will follow the flight trajectory as desired. I actually not noticed on this derivative at the beginning of the designing phase, and this makes my aeroplanes dynamically unstable for spiral mode. So I increase the L beta from 0 degree to 5 degree of dihedral angle. So my L beta is become larger, and that's make my spiral mode to be stable. After transform the state space to transfer function, we'll get 4 transfer function, which is shown at here, only 2. While the 4th transfer function includes the side slip angle, the roll rate, the yaw rate, and also the yaw angle. So what if the transfer functions, if we want the yaw angle transfer function? So it's easy. We can just multiply the transfer function of the side slip angle with -1 because they are oppositely directions. So now we can get both of the roll angle and yaw angle transfer function. So using the transfer function for roll angle, we apply positive unit step inputs at the aileron. The roll angle response is shown in the graph. We can see the roll angle reach until 41.9 degree, even with only 1 degree step input at the aileron. This means the paper plane will roll easily, even with little deflection at the aileron. Since this is a simple paper plane experiment, we don't have closed loop feedback system that can reduce the roll angles. So the safer way for my paper plane to glide is let the aileron deflection angle to be 0 during gliding. And this figure depicts the directional response of yaw angle due to negative rudder step input. You can see there is a sudden increase of yaw angle and in just less than 1 second, and the yaw angle decreases slowly with time and finally reach a steady state of 0.0342 at 180 seconds. Now, let us determine the lateral and directional dynamic stability using root locus plots. If you wonder why lateral and directional roots are in the same root locus plot, this is because they share the same characteristic equation, because they have the same denominator. And roll and spiral roots are real roots with negative value, while dash roll is a complex conjugate. 4 of them are located at the left half planes of the root locus plot, so they are dynamically stable. So from the characteristic equation, we can find the behavior of the paper planes in each mode. So the rolling motion is highly damped and will reach a steady state in a very short time. We can also see the time to halve the initial amplitude for both roll and dash roll is very short, while the spiral mode took longer time to halve its amplitude. By plotting the transfer functions of roll angle in Bode diagram, the frequency response for the change in roll angle to aileron inputs can be observed. The amplitude ratio is largest at the spiral frequency, which is at here 0.04, somewhere here. Yeah, the amplitude is constant the amplitude is constant between here, this range, and drop after 14 radian per second, which is Dutch roll among here. And at higher frequency, the aileron not effective anymore. And this is the frequency response for the change in yaw angle to the rudder input. The amplitude is constant at low frequency and slightly increased before reaching the spiral frequency at 0.0441 radian per second. The amplitude is constant between this range of frequency and drop after the Dutch roll frequency at 14 radian per second. At high frequency, the rudder is not effective anymore because the amplitude drops significantly. So, after all those calculations and analysis that took weeks to understand, would my control surface work as in calculation? Let's see the flight test. So, I would like to thank Prof. Swami to guide me throughout the assignment, and thanks all my friends who encouraged me to continue this work every times when I almost gave up. So, thank you everyone. And before I end, I would like to recommend this reference that I used in completing this assignment. Thank you very much.